is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space, fields and forms, math and voids. It all seems with one voice. It's home. Boundaries set, foundations laid. Sound was heard, matter made. Solar systems from afar. Names and numbers for the stars, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space. It's the Lord's.
And hello once again. Welcome to Sky Tour Livestream. It is I, Mark D'Antonio, here with you. At least I think I'm Mark D'Antonio. I kind of think that's true. And of course, I have with me our friend Daryl. Hello, Daryl. How's it going?
Hello, Mark. I'm well, thanks. How are you?
Awesome. Thank you. Thank you. Yeah, so we're going to start the night off by doing some of the stuff we normally do, and that's you look at the screen, it's a little bit bright here because we still have the sunset light out there right now. I want to say hi to Jeremy B and Junk and Michael. Space Junk is with us. How's it going, man? Andy Lino is here. Hi, Andy. Nice to welcome back, Andy. Andy's been here on and off. Nice to see you back. I'm going to try and set our low light mode. It's going to be a little bit of a few moments because we're waiting for the sun to get out of our view, the light. So we're seeing daylight here in the sky. In fact, I can show you. This is our view right now out in the desert. This is our AllSky cam you're seeing. If I move out of the way, you can see some of the data for the sun itself here. Up here we have the data for the cam, the date, time, exposure. And here's the moon settings. The moon is only 16.5% illuminated. It's minus 35 degrees below us, so it's down there in the east. And there's our compass rose, and we're in night mode. So as it gets darker, this is the sunset light that you can see here. Very sensitive camera. So that's how we have to do it for now. But anyway, that is our current, the auroras are quiet right now. And that's our current setup right now. And if we look at constellations, you can't really see them too well because it's not quite dark enough to see. But you can see Arcturus right there. That's quite clear. And the kite of Arcturus is right here. Okay, and then we have Hercules over here. And Corona Borealis right here between it and Hercules. All right, so we'll come back when we can start to see that again. Because the bright light of sunset is still bothering us. So let's see if we can actually take a photo right now. It might be a little tricky, but where we are, I can actually do a couple things. First I'm going to do is I'm going to do a analysis of our field of stars here. And it may be dark enough, may not be dark enough to solve for where we are. And if it is, we should see T Corboreal. I'm guessing it's that's right there, the blaze star. There we are. So it's dead center. So that was good. All right, that is our nova candidate. It's going to happen sometime this year or early next. We're going to continue to come in and watch it, try and catch it the day it actually pops off, and then goes quiet and dim for another 80 years. Well, that should be kind of fun, Daryl.
What's that?
It should be kind of fun if we can catch it.
Oh, the nova?
Yeah.
Sure.
All right, so Michael Hedrick is saying, popping a quick question. Did anyone hear why that satellite spread its guts all over the space the other? I do not know what happened. Was it a Russian sat, as you asked?
Yes, it was. It was a rather large one, I understand. Scott Manley said the other day it's been out of service for years.
Yeah.
Just orbiting up there, and he speculated whether a tank might have blown on the. I forget if it was just a satellite or a rocket body with it or what, but it was a pretty massive object, and he speculated that a tank blew or something of the sort, and it put a lot of junk out in space, a lot of pieces. They had to tell the ISS occupants to all get in their spacecraft and
that's right,
hunker down for just in case.
Alicia, hi. Alicia joined us. That I remember that the other day that happened. That's right. It slipped my mind. That's because I'm not up on the space station. If I was up there, it probably wouldn't have slipped my mind. Yep.
I wasn't aware when that happens. I think Manley talked about this too, that they have to get ready to go in case they are hit. Like they're fully suited up and
yeah, that's right.
Their finger on the button in each of their capsules to leave in a hurry if they have to.
I don't want to be the unlucky pair in the Boeing Starliner.
Yeah.
That spacecraft is having more troubles than you can shake a stick at.
Yeah.
It's sad because we want to wish them great success. We want them to succeed, but it's just seemingly not quite in the cards, you know.
That's Boeing for you nowadays. Boeing can't do anything right anymore.
Yeah. That's right. I mean, they're dropping parts off aircraft left and right.
Yeah. Their priorities. They change their priorities, and they're, it used to be an engineering company, and now it's a beam counter company, and plus they celebrate and worship all these social programs, which I won't get into, but
Izabela.
they've lost their focus.
Yeah.
Isabella's here. Hi, Isabella.
Hey, Izabela. We're looking at T-Core Bohr again, Izabela, just so you know. It's our it's our wonderful potential nova coming, right? That's what's coming. So,
Hopefully.
yeah. So we will check it out, and it will be really neat. I'm quite certain that it's going to be a most amazing object to see. All right, let's see. This is T Corona Borealis. I'm currently, it's not quite dark out there yet. If we look at our AllSky cam, you can see right here, once it comes up, that the sky is actually pretty bright out there. Oh, let me show you now here. So that's how bright the sky is right now. This is the sunset side. You notice the west, okay? And here, these lights here are the glow of Phoenix, 80 miles away. But that, again, we're getting a rim of light all the way around the horizon. This is going to drop down to just a subtle glow. So we should be good in just a little while.
The universe must still be expanding. Phoenix used to be 70 miles away.
Well, I actually recalculated it. I actually did a measurement, so... Alright.
Is that to the edge of town, to the center of town?
Well, yeah, that's the thing. I was going to the edge before, and I get 10 more miles when I go to the center of the Bortle 9. Okay. Alright, so this is... We're looking at T Corona Borealis. Well, we will be. Obviously, we can't see it right now because it's a little bit light, and I'm going to bring us down. What's going on there? Oh, it must be locked, and it is. Okay, now I can drop us down. Alright, so T Corona Borealis is right here. We know that because when we annotate the image, you can see it right there, known as the blaze star. There's also a galaxy up here. There's actually 2 galaxies. Actually, 1, 2, 3. There's 5 galaxies in this image. You just can't see them yet. Okay. Actually, this one. And then there's one right next to it, up there in the upper left. Then there's this galaxy pair. So there's a number of galaxies kind of right here. You see there's one there, and one right there. That's this guy. So we have one here, one there, and then another one just below right there. So pretty cool. Hey there, Tim F. Hey, Rocket City. What's happening, brother? You know? Izabela, thank you for your help today in working out the details for the app. I'm waiting to hear. This is just news for everybody. I'm waiting to hear from the people that we want to use our app through. The app that is called the STLS Skygazer's Companion. It allows you to sift through and look at every single thing we've taken pictures of on your phone, on your PC, on your Mac, on your Android phone or iPhone. And it's great because from there you can download all the images, you can download you can download all the raw data. It's really, really cool. And so that's something that we are trying to get straightened out now and figure out exactly how we're going to deploy. So when it's available, I'll tell you all the details. I'm sure Izabela won't be able to hold back, and she'll also tell you all the details, I'm sure. And Izabela asked a question. She says, I have a question that every time I forget to ask. I read that most stars in the universe are binary stars. Why and how a binary star? How is a binary star formed? Well, it's actually quite an interesting process. It actually depends on the number of protostars that form in the middle of a nebula. What's a protostar? It's that separate individual collection of condensing gas that's getting hot in the center, and some of those will orbit each other because they're so close in proximity, and the more mass you have that you collect in the center of your young hot gas cloud that becomes a protostar, the more gravity it has, and the more likely it is to attract something else. So depending on how far along it gets in its development, it gets to the point where there's other protostars that come through and kind of go into an orbit around them, and they can form a stable orbit around each other. Some don't, but most of them could do, and these become binary stars, sometimes trinary stars, quaternary stars. They can become sextuplet stars, quintuplet stars, and the more number of stars you have in a young cluster that are orbiting each other directly, then the more chances you have of a very turbulent early history, because the stars do not want to be, they want to be solitary. I say that like they're alive, but stars would do better when they're solitary, especially for planetary considerations. And when they're more than that, you have to solve the n-body equation, which is n is the word number of bodies all orbiting each other. If you have 2, we have laws that we can apply to that. 3, we have laws we can apply to that. You get to 4, 5, 6, 10, 10,000, 150,000, quarter million, like in globular clusters. And then you have something which is kind of troubling, because now you have to solve for the motions of every single star as it's affected by every other star. And that's why it's called an n-body equation. And they're really, really tough to solve. You need a very high-end computer. I remember solving an n-body equation with just 5 stars manually, just to see what was involved. And that was when I was working in astronomy. And I'll tell you this, not a fan. Not a fan. So I was very grateful when computers came along that could handle all this for us. We're going to try a shot here and see what we got. We'll see if we have any fringing. Actually, I didn't want to do that at 1 second. I want to actually make this about a 8-second shot. So 8,000 milliseconds. There we go. And now we'll live stack it. Clear it. And check it out. And we don't need the label there. We know this is T Corona Borealis. Okay. Let's see what we got now. Yeah, you need the Yeti back. Okay, so let's move this back here. And let's get rid of this guy here.
Yeti?
Yeah, the microphone that we got you, the Yeti. For better sound quality.
I don't understand.
Your sound quality was much better with the Yeti, is what I was getting at.
Was or is? I'm still using it.
You're using the are these new headphones, or he has a mic on it?
No, there's no mic on it. I'm using the Yeti.
Oh, you are?
I have the headphones plugged directly into the Yeti.
Okay, good.
Are you saying it doesn't sound as good as it used to?
Yeah, something we'll fix it. It's not a problem. It sounds very close to what it was. I'm hearing all this incidental noise, and I think maybe it's the something might have changed with the Yeti. We'll have to figure it out. It's not a big deal. You sound very good.
I better.
Yeah, I know, right? Okay, so there's our blaze star, and if we bring up our annotation, you can see it right there. Okay, I'm gonna save this image with annotations here, but I gotta put this up here and say this is our star T Core Bore. Okay, otherwise known as the blaze star. And I'm going to now save this image with the annotations on it. All right.
And it has been mentioned before. What we're seeing right now actually isn't the blaze star itself. It's the blaze star's partner, the red giant.
Right.
You can see the red tone in it.
Yeah, we'll zoom in on that. It's a good idea, Daryl. We'll zoom in just so people can see.
When the white dwarf blows, it'll be brighter than the red giant, and that's what'll stand out then.
Yeah.
I don't know if we'll actually be able to see both or not.
I don't think so.
I would, probably the red giant will be overwhelmed by the nova for a while at least.
Yeah, for a few days, the Nova is going to take center stage. So right here, I know this one little orange dot. Okay, interesting. But this orange dot is actually, as Daryl just said, two stars that are orbiting each other, and just like Izabela said, binary. And when stars are formed together, they form at the same time and they have the same age. But sometimes, based on their mass, it can be a little different. They'll burn through their hydrogen quicker and go on to the next phase of their existence. And when that happens to one of the two stars in the pair, one of them's going to grow into a red giant and then shrink down to a white dwarf if they're below a certain mass. All right, if they're bigger stars, more massive stars, then they may go supernova or whatever. But so these stars are probably stars either just about the mass or a little more massive than the sun. And so one of them has evolved past its hydrogen fusing stage, grew into a red giant, and then shrunk down to a white dwarf. Meanwhile, the other one started to do that process and went to a red giant. And when it got to a red giant, now we have a situation, because each star has this area, a spherical area around it called a Roche lobe. And it's the biggest the star can get before material bleeds away from the star. All right. And if you have a companion star, like in this case right here, the companion star is here, and you got this gigantic red giant that actually fills its Roche lobe. And so that means that debris, gas from that star, from that red giant, is going to leach through their common center of rotation and land on this white dwarf. And when that happens, a certain thing will happen over a period of time. That hydrogen gas on the surface of the white dwarf gets thicker and thicker and thicker. The stuff down below is getting very, very hot, and it gets hot enough to fuse. And when it reaches that magic point where it goes through a runaway fusion, the star brightens tremendously. This is the white dwarf we're talking about. And all that mass of hydrogen gas on this white dwarf doesn't put it over the limit for a white dwarf's mass, which is 1.44 solar masses. All right. And so if it's less than that total mass, then the star just goes through this runaway fusion, gets bright for a while, and then goes back down to being a white dwarf again. And the gas continues to land on the white dwarf the whole time until it takes about 80 years for this white dwarf to refuel. All right. And then go through its runaway fusion again. So we're waiting for that.
And when you see a nova like that, basically you're seeing like millions of hydrogen bombs going off all at once.
Yeah, that's exactly right. Now, the white dwarf's about the size of the Earth. And this particular star is... let me see if we can get that value. It says the distance is about... let me see here. I can't see where the decimal point is. Why? Maybe if I move it. Oh, 51? No. 2695. Okay, 2700 light years away, roughly. That's where this star is. So if it goes off, you're going to see it as it was when you see the nova. It will have gone off 2700 years ago, and the light train is just getting to us with that information. So that's pretty cool. All right, so I'm going to save this as it is. Can I get the coordinates for that comet, Daryl? Because I wanted to check that out.
Yeah, give me a sec.
Sure. I'm talking about Tsuchinshan. There's a comet that's now down in the constellation Leo. And Leo is actually getting pretty low. And I'm hoping we'll still be able to see this comet. Because we're looking way up high in the sky right now. And we're going to look down at the comet, which is in Leo, which is way down here in the west.
Ready when you are.
Okay. Let me just get over there. All right, I will take the right ascension, please.
Right ascension, 11 hours, 16 minutes, 27 seconds.
Okay. And let me move to the next. Yep.
Declination.
Yep.
+2, that's 02 degrees, 41 minutes, 30 seconds.
Okay. Now we're swinging way across the sky, so let's see if it'll be in here. Let me leave those in there for a moment. Do one more color correction.
It says it's computed for Colorado, so my location, so
Oh, okay. So
I'll be
it'll
off a little bit.
All right, we'll find it. All right, let's save this one more time. Save exactly as seen. And then come out of this. So there's our blaze star for tonight. Checked it out. And now let's go back to our low light mode. And in low light mode, we'll be able to see what the telescope sees with a little acuity that'll help us. There we go. Okay. Let's go now. And let's go to this location.
Doodah.
Yeah, I just realized I hit the wrong go-to. Alright. So now I say go-to, and it should go to this location. Mr. Django, what's up? Nice to see you. Uh-oh. Doesn't look like it's going the right way. It is not going the right way.
It's not good.
No, it's not going the right way. All right, let me go here and let me shut her down. Okay. Yeah, it was it got caught in a loop and it ended up going the wrong way. All right. So I'm going to turn it back on and let's see if we can get it to do this right.
They could hit a hard stop.
No, it didn't quite get there, actually. Now, here's what happened. So, I was trying to get it to go to the location we wanted to, but I hit this go-to, and that go-to is the wrong go-to. I had to hit this go-to here. So what I'm going to do is come out of here and we're going to have to do a plate solve, which is easy. Nice thing is the new mount system won't have any of this stuff as a problem. None of it. And now that I know we have a full backup in place, I'm being a little more cavalier with this one. Right.
Well, the comet moving into Leo. Leo's getting pretty far over in the west now, I guess.
Yeah.
If I remember correctly, when the comet's closest, it's either going to be a morning object or it'll go through a morning phase and
Yeah.
be back in the evening again.
Yeah.
It may be after perihelion.
Mm-hmm.
I'd have to look it up.
Okay, so. Well, that's a good spot to do a plate solve. A lot of stars here. And I should also pop out of this here for a minute. And let's do I'm gonna do a focus run here while we're here. We got plenty of stars for this. All right. Let's while that's doing a focus run, I'm going to set the parameters again that I want to set. That's going to help us. All right. Right ascension percentage for guiding. Declination, which is north-south. Oh, that's still 22. That's good. Okay. And let's go make sure that our other mode is off. It's on. We're going to turn it off. All right, good. All right, we're good. So now we'll wait. See, though, I mean, you know, something goes wrong. Got to have a way of fixing it long distance, right?
Hopefully.
Yeah. Cosmic Ray is using a C star. That's cool. I wish it had larger aperture because that might be attractive.
They talked earlier in the chat. I seem to remember hearing about this. Celestron is working on a 6-inch Rasa.
Wow.
That's going to be a smart telescope like the Sea Star.
That's very cool. Okay, we got a good focus here. I don't think we need to wait. We can just go to best focus, let it do its thing. Alright. Alright, and then we'll plate solve after that right here. Alright. There, now let's plate solve and figure out, let the telescope tell us where it is. And after it tells us where it is, it's probably going to be pretty quick. That's my guess. Yeah, right away. Look at that. All right, let's go over here. All right. Okay, we are currently. I'll need to have to say these coordinates again. Oh wait, maybe not. Maybe I can just bring them over here.
A suggestion, maybe?
Yeah.
Drive it over in the general area of Leo and then tell it go to, so it doesn't have so far to go, and maybe it won't get lost.
Well, that's not why it got lost. See this go to here.
Yes.
This go to here is a go to for the current object, and it was still in the process of doing that go to when I told it to go to here.
Oh.
And that screwed it up. I should have known better.
Don't do that.
Oh, where would I be without you? Okay.
Yeah.
All right, so here's what we're going to do now. We're going to do this. This is
You'll miss me when I'm gone.
1649. Yeah, and I'll be aiming 31.
Uh-huh.
All right, 16, 49, 31, And then this guy here is 24024. All right, and let me sync and make sure that that's right. Make sure it works. All right, good. It synced up fine. Numbers are now correct. Telescope now knows where it is again. Okay. So now that it knows where it is, I can come over here and put that comet coordinates back in. Let's do that part anyway. I'll drive over in the general direction anyway, but it doesn't matter. But I'll do it anyway because I don't want to risk any other garbage. All right, now let's head over to the west.
Michael, I don't know, per your question, did any of the science fiction authors ever predict remote control communications or telecommunications? That may be getting a little bit too fine on the question. Arthur C. Clarke, the British sci-fi author, he came up with the very idea of communication via satellite. Geosynchronous orbits and all that stuff.
All right, let's do a go-to and watch what happens.
And Jeremy, no idea.
It's doing it again. Damn it.
Oh.
Shit. Okay, I don't know why it's doing this.
Jeremy said, any idea when we will have another great comet like Hale Bopp? B-O-P-P. You never know. I mean, you know, comets are coming in and out all the time, and sometimes they show up and they get really bright, and usually they don't get that bright as Hale Bopp.
Yeah.
We'll just have to keep our fingers crossed. We've had some pretty good ones in recent years, and some that I know we didn't have such a hot look at up here in the northern hemisphere. They got a heck of a view down in the southern hemisphere. I forget, the one was Comet McNaught, I think it was called. May have been others.
I don't know why it did this again, so I'm just gonna go fix it again.
Interestingly, when Hale Bopp was on the way in, and I think people already had an inkling of how big it might be, how bright and all that, Comet Hyakutake came out of the blue a year before then.
Oh, that's right.
And turned into a great comet.
Yeah. Hey, well done.
Just about a year before Hale Bopp did. It was a surprise, and it was a very different appearing comet than Hale Bopp was, Hyakutake, but it was a heck of a sight. Hyakutake looked big and bright because it came close to Earth. It was a Midland comet, but it came close to Earth, and Hale Bopp didn't come very close to Earth, but it was a great big, really bright comet. And they both put on a heck of a show.
I remember Hyakutake.
Oh, yeah. That red 8-inch Newtonian telescope I built, I got first light on that telescope with Hyakutake.
You did?
It was great.
Wow. That's really cool. Okay, let's see here. And this is... Yeah, we're still at 02, 30, 32. Alright, let's sync and make sure this works. Okay, we should see the right ascension go to 1759. There it is. Okay. So that worked this time. And it worked last time too. That's weird. All right, let's try something else. Let's now go here and make sure that we're still connected. That could be another thing that's got to worry on that too. Let's disconnect, because this could have been reporting one thing and now it's going to get the data from the mount. There we go. That may have been the problem. Okay.
Comet should be right under the tail of Leo, if I remember correctly.
Yeah.
Star Denebola down in that area.
It's right here. Not quite there. It's up here. There it is, right there. Come on, move, move, move. There it is. There's Leo. Right there. Leo the lion. Roar. And there's the tail. And that star is Denebola that you're talking about. And interesting. Let's try something else. Let me go here and tell it to go to Arcturus, and let's see if it'll go. Because if we're having issues with this, let me actually move to the west just in case.
Well, Leo does look pretty low.
Yeah, it does. I'm not sure we'll be able to see the comet after all this. All right. Okay, so I have to do this first. Let's see what we got here. Okay, we still got that right. That's good. And let's go here. That should still be 22. Good. And now, when we come back here now, this needs to be shut off. And we're good now. Okay. Again, we're good now. We're good. All right. So let's go over to the west.
If you believe in relativity, D. Cruiser and Ray, I guess, for what he says, light speed is the universal constant. I mean, 186,282 miles a second or whatever. That is a constant. Rather than speed up or slow down in a vacuum, rather than speed up or slow down, it changes wavelength, redshift or blue shift, which we've talked about before.
Mm-hmm.
But the speed is constant. Now, as like for what Ray says there, Canadian PhD touting variable speed of light, a guy named Peter Beckman, who was the professor emeritus, head of electrical engineering at the University of Colorado in Boulder, he came up with the so-called ether theory.
Oh, yes.
And you've heard me talk about this before.
Well, I heard about the ether theory.
Yeah, he said that the speed of light is variable, and that the so-called ether is actually whatever the local gravitational field is. So it would still hold for us that we sense the speed of light as 186,000 plus miles per second. But if we went to, Alpha Centauri, for instance, the speed of light might be different, just on what the local gravitational field will let it be, I guess.
Which
It's an interesting theory, and there's a book out there about it, several books about it. And the guy, he's not a crackpot. He was, like I said, he was head of electrical engineering department, professor emeritus at the University of Colorado. And his argument supposedly did away with the need for relativity entirely.
Yeah, I'm not sure that. I'm not sure I buy onto that, but you know, is what it is. Okay, we are all aligned. Everything is good here again. I want to just make sure that we are here. Move that to the center. Zoom in. And synchronize. And that should go there. There we are. We are all synchronized now. Okay. Now let's see if we can let's see about Denebola. Can we go to Denebola? What's its altitude? 35? Should be able to do that. Well, let's try it out. See what happens. What's the worst that can happen? I gotta do this all over again. Okay, that's looking better. Yeah. There's Denebola. Okay. And that's 11:50:17. Okay. Good. And I'm going to center on Denebola. That's funny, Waldo. What's the speed of light? What's the speed of dark?
Do you want to verify those coordinates?
I'm at Denebola now. What do you mean?
The coordinates for the comet.
Oh. Yeah, let me just align on.
It looks like you say 17 and it's 11.
Oh no, that was no. What that is? That's different.
Oh.
That's actually the value for the plate solve I did. I've got to put those. I got to put those back in.
Okay.
This is good enough. So now I can come back in here. Go to Denebola. Zoom in. We're lower the horizon. Look at that. Okay. And now let's just align on this. Okay. Good. Okay. And now what I'll do is we're going to come back here now, as we said before. And now it's 11.
11:16:27, right, Ascension?
Okay, 11:16:27. Okay. And this one.
Declination?
2.
Plus 02.
Yeah.
41:30.
41:30. Okay. All right, so now we should be able to go to this because it's right nearby. I think we're all good. Okay, so it went down a little lower. And we should be able to see it. And we do, right there, dead center. Nice.
Hey.
Okay. And this is Comet 2023 Tsuchinshan-ATLAS. Okay, and it's right there. And it's be interesting to see this from last time we saw it, which was actually we noticed it had gotten bigger.
Looking at your telescope view, the upper one looks like you're probably just barely looking over the wall.
Well, yeah, I have at the far wall, I have more than I can see below 35 degrees, which is kind of where we're looking now. I'm sorry, altitude of 35 degrees. It's at 21 right now in its exact altitude, but the actual height off the ground is better than that, so we're good. All right, let me pull this over one. We should still have our same focus. Looks like we do. And I'm gonna probably may have some. It's 9:26 out there, so we may have finally got out of our light issue. Lubo in China, how are you? Nice to see you. Thank you for stopping by. Okay, we're gonna do a 15-second exposure here. All right, and it says it's searching. It's not guiding yet, but that could be because might have we have a full shot there. Okay, I'm gonna tell it to go. And I just want to see even a single shot is good. Bring up our live stack here. Clear this previous one. Let's see if we get one. Yeah, we did. Look at that. Let me get rid of this guy. This is way too much. Okay. Color correct. And let me...
Comet has moved on quite a bit. Actually, it's below the back leg of Leo
yeah.
now. Denebola being the tail.
Yeah, if we bring up Stellarium for a second and then back out, we can find where the telescope is pointing. It's way down here.
Yeah.
And look, this is our horizon. So we're in real crappy viewing. But notice, okay, the altitude of the comet right now, right, is 34 degrees. Okay, and we can still see it at 34 degrees. I'm going to come back into our histogram here and move this value over right to just near the peak. This is the black level. It's going to darken this up. And I'm going to move this down. This is the mid-level. That's going to reduce much of the noise. Still got a reddish haze, which, of course, we're right on the western horizon here, so interesting how this looks.
Izabela, the tail looks a little longer yet.
Yeah, it does.
Maybe a bit of a curve to it.
Yeah. Now I'm at 250 gain, so we're way higher than I normally go. Normally I'll go to 200, and the optimum for this camera is about 100. Hey Curtis Horn's with us. Yeah, look at the telescope leaning way over up there. Look at that, huh?
Yeah.
It's all right.
And the comet is brighter too.
It is.
When we were looking at it, it was 10th magnitude, and it's 9.8 mag now, according to the Sky Live.
Yeah. When you do an orange sharp mask, it's going to sharpen everything, including some of the noise. It doesn't really help us with the tail. It's not giving us any delineations in the tail. All right. Here we go. So need to have this star right there. It'd be very obvious when it moves. Right now, I could track the comet. There's a way to do that with this application, but I don't want to do that because I tried it before and it's not quite working right. So I'll let that ride for now. Let me just save this exactly as seen. I'm going to clear it. All right. And you see that star? I want to see in just a couple of minutes, we may see a difference in where that star is. Also, I'm going to reduce the gain down to 100 and then clear this again. Okay, so now we're going to shoot at 100 gain, and this will be we technically won't see as much of the tail, but I want to see if we can see a little more detail in what tail we can see without the noise, and we'll let a few come in. All right, so let's go over to histogram and align. And we're actually zoomed in, remember.
Mark, excuse me a moment, please.
Sure. Look, it already went past this star.
Be right back.
Okay, be right here. All right, folks, let's do this. Let's adjust our curves again. This is our black level. We want to move. I'm going to move this black level to just to the left of the peak, so we don't steal any data away. And this one, if it's close, it gets really noisy. Okay, as you can see. All right, but if we move it further away, then it gets less noisy, and there's a happy medium where you want to go. And that's what I'm doing. I apologize for the telescope snafu earlier. I don't know what happened. We have had many thunderstorms out there, but it seems to be operating now. That's all that matters. Izabela says it's a fast horse, this Comet. Hi, Jessica S. How are you? Good to see you. Starland, how are you doing? Starland is here from Atlanta. Nice to have you with us. If you guys haven't subscribed, please do so, because it's all free, and no one's doing what we're doing. This is basically 2 years of research in the making to get this to do what we're doing as it is. Hi, Fantasy. Oh, look, I had a satellite just zip through. Yeah, so this is 2 years of research to get this all to come to you like you see it here, and to try and get it all working. I'm 2,600 miles away from this telescope, and I'm operating it from the state of Connecticut, and it's out in Arizona in the middle of the Sonoran Desert. This is telescope 1. We have telescope 2 already purchased, and we're going to put that equipment 200 miles away in Benson, Arizona. Actually, we're going to join a lot of other observatories that are in Benson. And then we're going to have in the front yard here at my home in Connecticut, we're going to have a solar observatory where we're going to study the sun. I have a solar telescope, which I purchased, and we're going to put that in the front here with a tracking mount that looks only at the sun and only for the sun. It can't be used for anything else, which is fine. So this is pretty cool. It gives us the opportunity to study the sun and study the deep sky and deep space, and that's what we want to do. Oh, Starland, thank you for the love, man. That's nice. Yeah. And by the way, whenever we save pictures, like I'll do right now, I'm going to save this comet. I'm going to say save, and you'll see a green bar, and it's saving an astronomical file format. But then I'll say save exactly as seen. And what that's doing is it's saving a ping file, that, a regular graphic file, and this is that file. Here's the comet. So where is that going? Well, that's leaving our server out, or leaving our system out in the desert, heading up to the cloud and coming down and being deposited on our server at skytourlive.org. And that'll happen in about 30 seconds or less. And you'll be able to download that very picture I just showed you just seconds from now. And we give all of you these raw photos right out of our camera for nothing. And if you want an easier way to do it, even better, we're going to do a stream where we preview our application, our app called the STLS Sky Tour Livestream, STLS Skygazers Stargazer Companion. It's actually a amazing application written by Izabela Melamed, who's here in our chat. She's out in Bulgaria, and Izabela has done things like finding asteroids with our app. She's found stars that seem to have vanished. All right, and actually there is an actual professional project being done right now looking for stars that seem to have vanished. So that application, I've been talking to the people today. Look at how long that tail is. It's getting bigger. I've been talking to the people today that we're going to be hosting it, not hosting, but building it through. And Izabela and I were figuring out what we're going to pay per month and be able to set that in place so that we can offer you this application for your iPhone, for your Android, for PC, and for the Mac. I already use it on the PC. I use it on my iPhone as well. It's just beautiful, and it allows you to look, for instance, for every comet we've ever seen, whatever it is. You just put in the keyword comet. It searches through years and years of data and shows you every image of every comet we've ever taken. It's really cool. And then some. Obviously, you can look for anything. Literally, quite literally anything. Welcome back, Daryl.
Thank you.
All right, I'm going to push this a little bit. Okay, now I'm going to save that picture. Look at where the star is relative to the nucleus of the comet. Okay, so I'll save this. Save exactly as seen. All right. And I want to thank Izabela and Daryl for putting out the links out there. Fantasy says, I love the app. We actually had some folks that are power users of SkyTour using the app with us, and so they've been able to preview it and see what's going on besides Izabela and I and Daryl. And again, no one's doing this. This is becoming so deep and so dense in terms of capabilities. I'm just amazed that it hasn't caught on more. Wow. Yeah, Fantasy. When the app is actually made available online, then the one you're using will go away, but you'll have the new one. Hey, Christine is with us. How you doing? Sure, we're looking at a comet, Christine. This is Comet. Well, actually, I can show you the comet name. Let's go up here. I believe... Oh, I didn't save it, did I? No, I didn't. Okay, it's a Comet 2023 Tsuchinshan-ATLAS C/2023. I'm trying to do it all correctly. There we are. Okay. And now I'll put that up for you. There it is. And where is it? It's right. Here it is. And that's the comet right there. Right here. What's interesting about this, this is really interesting because we've noticed that this tail on the comet has grown immeasurably over the last weeks. And when we're looking at this little star right there, okay, versus where the comet nucleus is, keep an eye on that so that when we redo this image, look for where this nucleus is relative to that star. Comets move relatively quickly to our eye because they're relatively close to us compared to stars and other more distant planets and some asteroids. So the comet will definitely be visible moving against the stars. And that happens in a space of 10-20 minutes. All right, so let's save this. So why am I saving this and then getting rid of it? Well, because the comet's moving is dragging out the nucleus. And so it's going to make a dashed line for a nucleus because I'm tracking the stars, not the comet. But now when this comet comes up, let's compare it to where the little star is next to it. And
Christine had a question.
Okay.
Why are we having so many SpaceX launches lately? She lives in California and sees them from Vandenberg a lot lately. Well, that's a big question, Chris. Is it Christine, like the lady's name?
It looks like it.
So many SpaceX launches is because Elon Musk is doing his thing with Starlink. He's building his mega constellation of Starlink satellites, and he's got a lot of them to launch. As far as from Vandenberg lately, some orbits they shoot from Vandenberg. They're closer to polar orbits, I think. Closer to north-south, and they like to shoot them from Vandenberg because they head straight out over the ocean. Maybe I don't know what their reasoning is, but that and whatever commercial missions he's got.
Yeah, that's what I was gonna say. He's doing He's doing more than Starlink now.
Oh yeah.
The Falcon 9 is a very reliable launch vehicle.
Right now, SpaceX is doing the vast bulk of launches for the Western space program.
Mm-hmm. They are. Okay, this is interesting. I'm going to save this. We got 7. I'm not ready to save it yet. We're doing 15-second exposures. I'm going to just show you real quick in case if you're here for the first time. This is our telescope control section over there. This is the telescope computer right here. Currently the screen is blanked because it times out when it's not doing anything but guiding. This is the view of the telescope in the building. You can see the telescope leaning way over toward the west, which is that way. Okay, and this is another view of the telescope from down below, looking up at it. This is, well, I'll give you a guess who that is. This is our stacking screen. We are taking images one by one and then laying them on top of each other and stacking them to make the noise go away from the shots and bring out all the subtle details. That works very well. This is our camera control cluster up here, this whole area over here. And the most important elements here are the exposure right here and the gain right here. These two values set how the camera is going to react. How long are we exposing the sensor and how sensitive are we making the sensor? On top of it, if you look right down here, it's going to be hard to see. Okay, right there, you see a number that says temp. And it says -7 Celsius right now. Well, the temperature inside the building is 35 Celsius right now. And I've got the camera running at -7 Celsius. I'm actually thermoelectrically cooling it because by cooling the camera, you get less noise. Look at all these arrows. It's like, geez. Okay, so you get less noise in your shots if you cool the camera sensor, and that's what we're doing. Yeah. So that gives you a little tour. And the last thing is that what we do is we actually have a planetarium program that we use, that we hook to our telescope, and this allows us to run the telescope from this program. And notice that right now we've dropped to 27 is it 27 degrees? Where are we here? We are 17 degrees above the horizon. So we're actually pretty low right now, and because we're looking to the west out of the building, we can see, because the western wall is a little further away than this eastern wall, the western wall being farther away, we can actually see. We might get a little interference, but that's about the limit. We're not going to go any lower than this. So I'll save this and save exactly as seen once again. And again, this image will be up there in a directory that's marked C 2023 Tsuchinshan-ATLAS. That'll be up on our server, which you can get to by going here, skytourlive.org, right there. We are a non-profit. We depend on people helping us. Skytourlive.org is our portal. To the upper left, you can go to Skytour Livestream, this right here. And to the right, you can go to our Patreon and join us. I mean, we have a number of really cool patrons, okay? Not a whole lot, but we're building. And we want to actually see our numbers get a lot higher and get a lot more people, because it's because of the people who donate to our Patreon, this in here, that we can do what we do at all. All right? So please consider, I mean, hang out, check it out, and if it's right for you, hey man, consider joining our Patreon and help us out. You know, we have $3 a month, $5 a month, all the way to $200 a month, and believe it or not, we have people in all those. So it's actually very important to help us out for us, because we're not making any money. I don't make any money on this. This I do because of passion, not because I'm money grubbing. I'm an astronomer, a professional astronomer. We care only about the data and educating people and showing them the beautiful universe out there, the dynamic universe. I'm going to say this one more time. Yeah, save it exactly as seen. Now I'll clear the list. And
hit that thumbs up while you're at it, too.
Oh, yeah. Help us with the algorithm. Yeah. And more satellites. Okay. I'm going to terminate our view of the comet because it's really low right now. It won't hurt anything, but I prefer to look at things that are a little better placed.
I didn't know you could get that low on the west.
Yeah, the wall. We're part way in the wall. A little edge of the telescope is hitting it.
I'd almost wonder if you couldn't reach Comet Olbers if you looked soon after dusk.
Might be a little bright.
Yeah.
Okay. So let's go and check something out. Let's see if we can get up to this guy again, and from there we'll go someplace else. So the telescope should do that and move us up to the constellation Hercules, kind of in the northeast here. And it's, oops, sorry. We should see the cluster. I'm of course at 45. Let's go to 25 and see if it's in the view. There it is. Not bad across the sky. All right, so what we're going to do is we're going to move it down into the view. This object was just stunning the other night. I literally, it took my breath away, and I've seen it maybe 150, 200 times in the last couple of years, maybe more. And that's a low number. And it really was beautiful, and so I want to show it to you again in case it looks as beautiful as it did. First, let's go look at our night sky and see what we got. Hey, there we go. Here's some clouds down here. Notice they're dark against the sky because we don't have light pollution out there. Here's the lights of Phoenix far, far away. Here's the summer Milky Way rising right here. And to see constellations, we can see them right like this. Now we can see them. There's Deneb. There is the constellation. Oops, sorry. There's the constellation of Cygnus, the Swan. Let's do it this way. Here is Deneb right here. All right. This is down here. Let's see. There's Altair, and Lyra is here with Vega. Let's look at. There's Vega. Let's do this. Okay, here's Vega, and Vega in the constellation of Lyra with Deneb in the constellation of Cygnus, and Altair in the constellation of Aquila, the Eagle. These form the summer triangle. And you'll see Vega come up first. All right, and that's after this one here, which is Arcturus, starts to set. Vega takes center stage and comes up. It's very nice.
Den of Vega and Altair make the summer triangle.
Yeah.
And when you see Altair there, the star right next to it is called Terra-Z.
Terra-Z. Yep. Were you able to hear me before? Because I literally just said, before you said it, these are the summer triangle stars. Did you not hear me say that?
I don't know.
Okay. I just want to make sure you can hear everything that's going on, too.
I can hear.
All right.
I probably wasn't paying attention.
Okay. All right, so let's get out of this and go back into our view now of measure 13. All right, this is our low light view. And we're going to lower this down just a little. There we are. Okay. Now that it's doing this, it's guiding. And you'll see it says searching, and it takes about 14 seconds or so for us to start seeing numbers here. Those numbers show that we're guiding in right ascension, east and west, and declination, north and south. All right. And that is very important. And I'm going to set us in motion here with a 20-second shot. And a Starlink satellite. That's definitely Starlink. That's the length in a 1 second shot that we expect. Okay. And now I will go into the live stack. We're now guiding, as you can see our numbers. And we've got this histogram way up, and we've got this one here cleared, and we are 4 seconds, 2 seconds.
Excuse me.
And any second now. There is measure 13. Look at that. Looks really pretty. Let's do some color correction. Don't really need it. It's looking pretty good. Very nice.
Uh-huh.
Yep. Zing. Yep. Welcome to satellites. Causa Gray got sucked into Cygnus. You're not supposed to take pictures of the Hale Nebula, Ray. You know that. Ray's always kidding with us about the fact that we like to take pictures of the Hale Nebula, a supernova remnant in the constellation Cygnus. It's really beautiful and colorful. Nice. And we're just going to take a few of this. I don't want to go crazy in here. M13, a GC or a globular cluster. In our app, you would search for M13 or globular cluster or GC because we've internally defined those things. Izabela did when she was building those values in. Ray went to the dark side. You are part of the rebel alliance and a traitor. Take him away. That looks good, Daryl.
Yes, it does.
Yeah. Let's see if we've lost any images. None so far. We're guiding with a full width f maximum filter, which allows us to specify how much star out of roundness we will accept. And I have it set to very little, so our images for the stars will be round for the entire set of exposures. And even if we get a bad one, it'll just be rejected, and you'll see a rejected frame right here in that little spot. See, frames rejected, 0.
Another night, still night.
Yeah. I noticed.
Starline asks if we might look at Messier 27.
Oh, yeah, let's go see if Vulpecula is up high enough. Well, we'll do that while we're looking for this. Let's go see. When we say up high enough, we have to consider that we have to look. Yes, this is like way here. And this is the veil.
Vulpecula's farther up to the right.
So we have it right here. So zoom in, see how high it is. This one, I can't remember which one it is. If it's this one, must be that one. Oh, there it is. Duh. I was looking at the wrong symbol. I apologize. We're kind of near it. Let's see what our altitude is. 39. That's a little borderline for us. And I say borderline because it's going to be looking through this part of the building to see it right now. So we're not quite there. But don't worry, we won't rush summer. Those will be overhead before long. It won't look that good from this location anyway because it's a little bit low. Actually, let me show you where it is specifically. Okay, so here is Deneb, here is Gamma Cygni, and this is Cygnus the Swan. In fact, this is the Northern Cross right here. You can see these stars, 1, 2, and then Albireo. I'm looking for Albireo. There it is. So we got these three.
That's not Albireo.
Oh, is that's not Albireo?
Next one down.
This one is?
Yes.
Oh, look, we got a plane. Maybe it is. And right near it, this is where Messier 27 is. So it's still more toward this region, a little bit low. So it's not really in a good place for us right now. All right. But that's good. Good suggestion. We'll keep doing. We'll look for that because I have not imaged the Dumbbell Nebula yet with this particular camera. This is a new camera that we added, and it's got a lot of tremendous capabilities in it. M13 Globular Cluster labeled as such. Save. And save exactly as seen. Okay. Beautiful. All right. So now up on the cloud and then down at our server, this will be the image you get when you download it. Very cool. All right. So now we're going to come out of here. Go back to our low light mode from our deep sky mode. And then let's go see what else we can go see. There's always something to see. I wonder.
There's the Eagle Nebula.
Yeah, we have that. I was wondering if we can go check it out. I gotta check its altitude.
It's serpents, but it's the tail of the snake, and I don't know if that'll be high enough yet either. Over Sagittarius.
Yeah. Yeah, this. Some of these won't be ready for us yet, but moving further up here, we should be able to. We should be able to capture that. That's Scutum. There's the Eagle. Let's see what its altitude is. 34. A little low yet, I think. But we'll try it. We'll try it. Let's see what we get. What's the worst that can happen? We can't see it. Alright. There we go. Let's go see if we can capture it. It may be looking a little more toward the building. Oh, we might just squeak this one out. We might just squeak this one out, guys. Let's drop this down. There it is right there. How about that? Okay. Alright, so we are gonna head north a little bit. And this is the Eagle Nebula. If you haven't seen this yet, you're in for a treat. This is quite a beautiful nebula. We may have a tiny bit of the building interfering with us, but it's okay. Oh, you'll like this if you haven't seen this before. Remember the Hubble shot, the Pillars of Creation? That's these. Doesn't look much like that right now, but you will see that it is. Alright, I'm going to move a little bit more north here. Okay. I'm going to zoom in just to check our focus. I'm going to look at our stars, see if we need to refocus. Doesn't look that bad. Let me try something here. Okay. Alright, I'm going to zoom out and do a quick focus. Alright, I'll do a quick focus here. This object by far is going to make your night if you haven't seen this yet. Boy, I better deliver now, huh? Hey, Louis Ta's with us. Sam S., how you doing? Sam, you've been here a while. I don't think I said hi to you. I apologize. Michael Hedrick's back. Judy M. is here. Hey, Judy. We're making our focus curve. That's what this is right here. We're just going to make a curve, and at the bottom of the curve, it's going to interpret the best position. It's not going to be this the discrete triangular position. It's going to be whatever's somewhere in between. And that gives us our exact focus. You can see the bottom of the curve right about here. And one or two more data points, and we're going to actually get a line that's right about here. We're right about there. There it is. And if I let it go to the end, then it'll automatically go there. But I'll just tell it to go to best focus now because it won't change much. And so now it's going to go all the way across and all the way back to find best focus. There we go. So now we'll have perfect little stellar points of light. Okay. So that's done. So now what we're going to do is we're going to do something a little crazy. We're going to make this a 25-second shot. And when you see it, you'll say, wow. This is known as a stellar nursery, a hydrogen alpha, which is a atomic transition to hydrogen. It glows red. And so you see the red gas in the nebula. And it's really, really pretty. Let's get rid of this. And now we should be able to see our first image. Oh, look at that.
Nice.
Beautiful. Little correction for the color. Wow. Here are the pillars, folks, right here, the pillars of creation. Why do we call those the pillars of creation? I'll tell you why. Because these pillars, with this one being closest to us, I think, or is it this one?
No.
This one.
That one, the foot.
Yeah. These pillars are composed of dust. And this dust is made of carbon and silicon atoms and other materials, and then they have ice on them in the dark. This is all dust out here as well, silhouetted by the brightness of the nebula, this glowing gas. So this region, being a stellar nursery, here's the stars that formed in here, among others. They have very powerful ultraviolet light, and it shoots out in all directions in 3D. So some coming toward us, some going away from us, some going to the sides. And what ends up happening is it causes the hydrogen gas, number one, to ionize, and that makes it glow red eventually. And then what it does is something else. It causes erosion of the dust because of the powerful stellar winds. And those stellar winds push away lightweight stuff, and where the stuff is densest at the ends here, that stays and protects what's behind it in the lee side, the back side of this pressure from the stars. So that's we call these pillars. We also call them a number of other names. Okay, but these pillars right here, all right, or stalks if you want to call them, whatever. These are really, really made by the stars themselves. Let me just process a little more so you can get a better view. And let me see where it wants to go. It's going to go there. I'm going to pull this in a little bit. I can see that we actually should have let the focus run continue because they're not quite in focus. So for all this beauty, I'm going to stop it because we have to redo the focus run. I'm sorry about that, but you'll be happy for it in just a minute. So let's go to 1 second. Our nice yeah, okay. Get rid of this stack. We don't need it now. Okay. I'm going to take us down and refocus. I noticed the stars are out a little bit. So what happens when the telescope moves? There's tiny sub-millimeter size shifts in the mirror, and when that happens, those sub-millimeter size shifts will cause it's called mirror flop, and it causes very pronounced differences in our focus. And we want to prevent that. So let me just drop back down here and start the process again. And this time I'll let it run. And I've been joined by my dingo. My dingo has joined me. What's up, dingo? Anybody eat your baby? Okay. So, I noticed when I looked at that image that it was actually a little soft, and so we have to change the focus to make it more proper. Lewis Todd says those stars in the nebula, in this nebula, protostars are already main sequence. Depends where they are in their evolution, but sometimes stars that are protostars haven't really winked on fusion yet, so they're not really main sequence until they're fusing hydrogen into helium. So we have to be careful with the terminology. It may or may not be that the stars are main sequence yet. Okay, it looks like it didn't catch the center line here, but we'll find out.
The bright stars we see in the area are main sequence.
Yeah.
They're energetic stars, and their radiation and stellar wind, I guess you might say, mostly radiation, that's what's forming the pillars.
Yep.
When we look at stellar nurseries all over the sky, we see pillars like that. And the pillars always point toward the bright stars that are shaping them.
That might do it.
It's a pretty funky looking parabola.
Yeah, no, it actually missed the focus.
Yeah.
Not sure why, so I'm gonna reset it, and I'm just gonna bring it out just a couple of notches here, and let it do it again. Okay. Our spider web in here is moving around, so we got a little wind out there. And wind will affect our focus capability too. The other thing is, if the telescope is impinging on the wall, we might have an issue as well. I don't think we are, though. I don't think it's impinging. All right. If any of you got any questions, by the way, while we're waiting, feel free. Let's see if we yeah, I don't know why it's not doing the focus. This is right about where it should put something right about there. I think wind is killing us, right? Not killing us, but it's actually causing a problem out there.
It seemed like it was quite still out there not long ago
I know, and
when you did that full width half maximum thing.
yeah, but you look here, and you got the spider web bouncing around in there.
Yes, I see that.
You know, it could actually be another thing too. Let me just take us off of this for a minute. It could be the fact that we've got a nebula here. That could be part of the problem, but maybe not. Let's find out. Let's drop south a bit. Okay. Actually, you know what? That was the wrong way to go. I'm going to go... Let's go a little faster and let's go north. And then we'll come back to this. I want you guys to get a really good picture of this thing. So let's get out of here and just get the blank stars. There we go. Okay. We're going to reset this. Okay. Now let's do it again. I also should wait until we start guiding, but I'm just going to go for it. Wait, okay, we're guiding. I might actually have had too many stars in the view. I'm at a loss to explain what it's doing. This works so well. It might, there could be a million reasons, but I mean, the focus is getting better though. You know, our star count's going up, so it's focusing on more stars. Now it's going back, and it should probably put a line right there, so... There we go. Okay, so it found it there. It was a matter of having too many stars in the view, actually. Thank you for putting that up, Daryl.
Sure.
Okay, alright, so now I let it go to the end and it focused explicitly to our best focus point. I may have closed it prematurely before as well, so that's another possibility. Alright, so now we can go back south and start the process of showing off. I like showing off the Eagle Nebula. It's really a cool nebula to show off. And this is Measure 16, M16 The Eagle. And it's a emission nebula. I use that as an EN. EN stands for emission nebula. Okay. Let's zoom in and check our star quality. I suspect this should be good. Star quality is excellent. Alright. All that modeling you see, that's noise from the sensor. I'm going to bring this up, our gain now. I'm going to bring it up to 200 again. All right. And now what we'll do is we're going to go back to our 25-second shot. 25S works as well as 25,000. And we're off. And we'll get rid of this low light view and go to our deep sky mode. And we're at the deep sky mode. Our counter is down there on the right. You can see it right here. There's a progress bar. If you're using a high definition TV, you can probably read this. Okay. And okay, that last image was rejected.
Yeah.
I'm wondering why. Maybe that's probably the wind I was talking about.
Yep.
Okay. Ah, look at that. Worth the wait. Okay. Yeah, see, no soft focus anymore. This looks good. And what we're going to do is bring our black level curve to just before the peak. Darken it up. And then take this one and move it down. This is the midline, mid-range. And that's where we want it. And then we're going to color correct. Get rid of the green in the sky. There we go. Look at that. There's the whole eagle, guys. The whole Eagle Nebula. And those are the pillars of creation. You can see them better now. Let me zoom in now. I know we only have, we've rejected 3 frames here. So I got to raise the bar here a little. Wow. As soon as we get a second frame, the noise halves right off the bat. So you watch if a green one comes in. We got another. We're getting some wind out there right now. Thank you, Michael. It is gorgeous, isn't it? That's right, Fantasy. Stellar Nursery. Here's the stars that were born here. They're hot and have ultraviolet radiation to cause this hydrogen gas all around the glow and to carve these pillars with their stellar winds. All right, well, we're going to raise the bar again to 8.57. When we're on the equator, 8.57 might be okay. Or close anyway.
I think it was Starman who mentioned earlier, somebody, the Webb telescope, JWST, recently released a 3D look at the Pillars of Creation, SJ16.
Oh, yeah, that's right.
Yeah, I sent you all the
yeah, that was really
links.
That was
there were several videos of it. One was from JWST, one was from Hubble.
What's going on here?
Ultimately, I guess they're all from the same place. But some of them were multispectral also, which really highlighted details in the nebula. The JWST image right at the tip of the eagle's beak, that middle pillar, they showed a star just coming to, whether it's a protostar or had just achieved fusion. Right in the very tip of the eagle's beak is burning bright red in the Webb image. Looked really cool. And when they figured out the 3D of it, however they would have done that, can we zoom on it a little bit?
Yeah, just a minute. I'm trying to figure out why I'm getting red exposures here. And no more exposures being captured.
Hmm.
I wonder what's going on. It did one, and now it's just yeah, we can zoom. It's not gonna be good though because we're not. It's still noisy.
I wonder what happened.
Yeah.
When you see the, can you see the eagle there, folks? Generally, it's the part right in the center. The object on the left is its wing, that hooked or curved shape. Then its body and its head is the middle pillar, more like the dark part. But yeah, the middle pillar there, that's the eagle's body with its head up at the top right, and the tip of its beak right at the end. And then the eagle's foot is the third object, the one on the lower right. That's like the eagle's foot. And when Webb did the 3D construction of the nebula, the foot is actually the closest part to us. And then the body and head of the eagle is behind it, farther away.
Yeah.
And the wing is farther away still. So they were like stacked in space.
Yeah, I've cleared this because I gotta figure out why that happened. So we're gonna just do a 20-second shot here and see if that makes a difference.
Still being a bit rambunctious tonight.
Yeah, I guess that's true. I want to use my full width half maximum filter. Well, there's two stacked. See, it keeps saying searching. So what's happening is the wind is making the guiding fail. Yeah, we're getting there now though. All right, so we got 3 stacked, no rejection, so we're good now. As we stack more, this gets better and better and better and better. All right, so we're hovering there. So I'm going to, for whatever reason, have to restart that exposure. So here is where we'll have perfectly round stars with this limitation on us. So this is good. And this will be the last object tonight, but we will be getting a good shot of it for you all. Look at this. This is gorgeous. This is really showing nicely. And this is really nice too over here. Look at that.
If you look down under the eagle,
Down here?
a little higher, right about where your pointer was, there's another big pillar right there.
Oh, this one?
That one and the one to the left of it.
This here?
The one in the middle, right there.
Oh, yeah.
Those are all pillars. You see they're all pointing up toward
sure.
those bright stars.
Yeah, they are. Yeah.
It's actually nice down below there.
It is.
You've got a very red edge on the that central dark cloud below the eagle to the lower left. That right there.
Yeah, I got this too.
And you can see the fairy up above to the upper left of the eagle.
It's this right here he's talking about.
Yeah. Always reminds me of a hood ornament on a car.
I guess it does.
Tipped sideways.
All right, so.
Or like an Emmy statue or something.
Yeah. Oscar statue melting.
Oscar.
All right. So I'm going to pull this down just a little bit. Just subdue some of the noise a little. Look at that. That's pretty. Now each of these dark clouds you see are clouds of gas and dust. Okay, there'll be hydrogen gas in here, but there's also lots of dust, and there's not enough hydrogen gas in here to outshine the density of the dust and get through the dust. So even though we might have ionized hydrogen somewhere in these dark clouds, there's enough of the dark dust that it's going to prevent any of that from being seen. And this is much denser out here. And this is where we were born, folks. We were born in the dark. This is where every element in your body was, assembled when the planets were made, because they were made in the dark dust motes in the universe, not in the bright emission nebula like this. The planets aren't made in here. The planets are made in the dusty areas that are shaded and kept safe by density of material at the top of the stalks. So down in here somewhere, you could be getting planets forming around stars. Hello, Catherine Mezek. How are you? Yeah, those are the pillars of creation that Hubble shot and that James Webb then shot.
Can you zoom back out and go up to the upper right? There was that one dark cloud with a larger red cloud behind it. That right there, up at the top.
Yeah, this guy.
Yeah.
Yeah.
And that dark cloud is closer to us than the big red cloud is behind it.
Correct. That's why it's occluding the cloud behind it. And that's what we see with the Orion Nebula. That's what we see with this dust here. This dust is closer to us than the background stars. What's interesting is, because, let me just bring this back up here. If you look at this one right here, this little tiny one that is the foot of the eagle, right?
Yes.
This interesting guy, notice how dark it is? It's dark because it's closer to us than these stars. So we're actually noticing that we're seeing a dark side of it because of the fact that the starlight is not shining on it. This one, the starlight's shining on this area, and it's also got some hydrogen in here that's ionized. So this stalk is sort of in the middle. This stalk is somewhat shaded from these stars, so it's closer to us than this guy probably. And then this guy is closest to us overall. And we're seeing that just because of that reason, because of the three-dimensionality of the universe.
Yeah. And if you look on YouTube, those videos should be easy to find. Again, that area to the lower left of the eagle, where those dark pillars are.
Yeah.
There's dark clouds with strong red edges on them. It reminds me of the horse head in Orion.
Yeah. Well, same processes are driving that drive the horse head in Orion. You've got these sharp edges, and then you've got the ionized gas all throughout. And the sharp edges are, well, they wouldn't be sharp if you went near them. They would be sort of gradual, like a cumulus cloud looks sharp on the edges from the ground, but if you get up in a plane, you sort of enter the cumulus cloud and say, am I sort of entering a cloud now? Because you don't really see the border anymore. So that's pretty cool. Astro Lynn, hey, what's up, brother?
Can you move your pointer, or is that, to the left, to the right, below center, a little bit farther to the right, down a hair. Keep going, a little bit to the right, a little bit at a time. Right.
Oh,
there.
This here, yeah.
That whole dark edge there has that sharp red edge against the dark edge.
Yeah.
And that in particular reminds me of what we see.
The horse head.
Next to the horse head.
Yeah. And this is interesting because we can actually see, you know what? I'm going to enhance this. Watch this, guys. Ready? Watch this. Wham. There you go. How about that? I just ultra enhanced this really quickly, and now you can see that this pillar right here actually stops right about here and is dangling in space. And it really is. No, Astrolin, this is the Eagle Nebula. You can tell because we see the eagle right in front of you. It's not the California Nebula, no.
Very pretty.
Yeah, very nice. And by adding these extra capabilities, notice that we see a lot more tendrils and other interesting features in this nebula. It's just something else. Really pretty. Okay, 22. I'm going to save it here. Michael Hedrick has a question. Okay, Michael Hedrick, what's your question? Did you know that if you were a jumping spider, you could see the universe in extra colors, since some of these are trichromats and some have trachomats.
Tetra.
I couldn't read that word. The screen is blurry on my monitor. Tetrachromacy in their eyes. Wow.
4 colors.
Mm-hmm. Well, it'll be very interesting, yes. And when dogs look at the world, they don't see certain colors the way we do. They see very little red, if I recall. They see green and blue, which I think is interesting. So when dog food companies make these beautiful red treats, dogs don't see them that way. They're red because they look good to you. So what do you think of this, guys? This beautiful Pillars of Creation Measure 16 Eagle Nebula that we're looking at. Yeah, Fantasy, it is a more muted color palette for dogs. Yeah. This part of the fairy that Daryl's talking about in the chat is quite dark. Wow, this guy is now very clearly separate. Very, very interesting. Yeah, that's really pretty. Let's get right in there. Look at that. I also wanted to add something else. You see these little dark spots here? These are areas of concentration of dust, and it's possible that these are self-collapsing due to their own gravity, and thus becoming Bopp globules, which are these little globs of material that can become planets at some point in the future. Really neat. Now, if we were shooting this in black and white, it would look like this. Not so exciting. Okay. But we're shooting it in color, so we get this. Also, if you want to see more details, sometimes it's beneficial to do this. And that's turn it into a negative, and then you can see details like that extra dark nebula and how separate it really is. Okay, so doing the negative is very helpful. I used to use that when I was getting a degree in astronomy. That's what we did a lot. Many of the charts I have, and I still have here, are charts that are negative charts. Stars, everything, all negatives. Easier to see the data that way. Very cool. Okay, we're at 32. Gonna save again. Save exactly as seen. This is looking nice. Let's see.
It is.
Drag this down a little more.
Nice picture.
Mute the noise some more. Saturate the colors a little better. Look at that. This is a good point to look at this because you can almost see a three-dimensionality in here. Like this is a large cavernous opening through which you can go, and this is closer to us than what's back here. Over the precipice and down you go. Now these stars are carving out this cavity. That's the whole point. And where there's dense dust, they don't carve out. They actually protect what's behind them. So we're seeing that happen here, but where there's just gas, the stars basically push away the gas. That's what we're seeing.
It's exactly the same thing as when we look at the Rosette Nebula in the wintertime.
Oh, precisely, yeah. Precisely. So we back out. Then we'll do this.
At this scale, when you see the edges of the red up toward the top of the nebula, and then all the dark that's not dark space, that's dark clouds.
Yeah, this is a
that aren't illuminated.
This is a very dense region of dust in the universe. Not everywhere you look in the sky is like this, but there are certain regions that are. This is one of them. This is the oddball. This thing here is caused by this cluster of stars. All right, so we have all kinds of these deep, highly detailed features out here somewhere as well, but we just don't see them. You know, maybe not so many pillars until you have stars that are forming, but you have all these intricate clouds. I love this right here. This region is very interesting in here. Look at this. Holy cow. Maybe it's just, this almost looks three-dimensional, like we're riding along a surface, going deeper and deeper into the page. Wow.
Look at the base of the fairy now.
I hear.
Yes. That also it's kind of a dark triangle pointing to the right, but again, it's got lighter edges around it.
Yep. Really cool.
And the fairy's coming in rather well.
Yeah. Now we're at 41 shots. And what's interesting is that in order to cut the noise in half from this point, we have to go to 82 shots. We have to double, sort of a rule of thumb, double the number of shots in order to make them cleaner from noise. So when we do one, when we take the second image, we've halved the noise. But when you get to 10, to get better than 10 shots, you have to go to 20 and to half that noise. That's a rough rule of thumb. Depends on a lot of things, like cameras and so forth. This is amazing. Look at that. That's something else. Okay.
If you look at the eagle's wing, right in the near the corner at the top of the shape of the wing, there's a star in there.
In here?
Nope, down in the dark part of the wing.
Here?
Right there, there's a star.
There's one right there, too. See it? Right there?
Yes.
One there. Now, what is interesting is, in this space, we only see, maybe 100 stars. But when the James Webb looks at this space, literally just this space, there's thousands of stars in here that are forming in the dark. You don't see them. That's what's really interesting about this nebula. And any nebula, for that matter. I can't wait till the Orion Nebula gets covered by the James Webb. Wow. So as you can see, I went full screen to give you the opportunity to see this. I want to see where we are. We're at 48. And we'll soon be at 49 shots. There we are. We're going to go to 50 and save it for one final time. And it's 1:45 a.m. here, so I'm going to go to bed. I wish I had a cot in my office here. I would just sleep here. Okay, 50. So we're going to save it. Now, if we want to make one that has half the noise, we would go to 100. But there's a... You see, you can see some of the noise up here. But that noise can be alleviated in other ways as well. Let's drop this down by half the distance and reduce the noise further that way. Look at that.
This will make a nice processed image.
Oh yeah, it's already looking beautiful right here.
Yeah. Keep the red.
Oh, I'll make it green. I'm kidding. All right. Well, folks, I hope you've enjoyed tonight and checking out our beautiful summertime interloper here, our beautiful Eagle Nebula. That looks 3D. I mean, it really does look 3D, you know?
Yes, it does.
You come in here, it looks like we're looking down the hole here, right in here. You know, like way down in the hole down there. And then we come out to look at this. Okay, but then go down the hole in there. It looks like in the same thing here. And with that, we have a lullaby, Twinkle Twinkle Little Star. That is for all of you who should probably be in bed, some of you. Izabela's just getting up. So I wanted to thank you for joining us tonight. And we will be back on the next clear night. And we start late because the Milky Way comes up late. But again, live, universe live in real time. That's what we show you. Hope you enjoyed this. Please consider joining our Patreon and helping us out. We could really use the help, you know. And if you can't, that's fine. It's all free. We enjoy your company. Come along. Come one, come all. In any case, this photograph that you're looking at right here will be available just as you see it. I'm going to save it right now and then save it exactly as seen. Right, so now what will it look like? I will click on it. This is what you get when you go there and look at it. And you can zoom in on it, okay, and check it out, you know, and see it. So this is what is available to you up on our server here in just a few seconds. So enjoy it. And our server where? Our server here, skytourlive.org, right there. So join us, and we will see you on the next trip into the universe, guys. So thank you for joining us, and have a good night, everybody.
Good night, everybody.